Alright, so this is our Project 4. This is us testing our libraries to make sure that it works. First we're going to compile everything, and then run our tests. As you can see, all of our tests pass, and now we're going to be moving on to our diagram, which is going to explain this piece of code we were given and what each function does with open, read, and close.
So basically what's going on in this function is we are trying to open a file for reading purposes, and it is loaded based on some file descriptor that represents what that file is and where it's located. So at a file system level, our file system keeps track of all of these files using some type of bitmap that represents where they are in location, and this bitmap is also in correlation with the inode block, which is a block on disk that represents all the inodes, which represent the file descriptors for each file. And in this inode block we have X amount of inodes. Each one of them represents an individual file descriptor. So upon an open, our file system will first search through that inode block to see if that associated file descriptor is inside our file system. And if it is not, that means the file is not actually there, so we need to create a new inode. And this new inode will be generated into our inode block, and along with that, our inode bitmap will also be updated. So an inode, let's say we wanted to create a new inode, and that would be our second inode. So then in this bitmap, this 0 would turn into a 1, marking that this is no longer a free inode. But because this, we are assuming that this file is already located, or it's already been created in our file system, what's happening is that this will open that file descriptor based on where it is in the inode, and it will open the pointer to that file into some buffer. Now that we have that buffer and the located file descriptor along with its offset, we can actually start to read from that file. So when we read from the file, we simply go to the information of that inode of that file descriptor, and we check the associated blocks that are pertaining to that inode. That inode might contain direct pointers to blocks 6, 7, and 8. It could also contain an indirect block, which contains more pointers to even more blocks. But each of those numbers in the direct pointers represent the certain blocks that we should be looking at for the information of this file. So upon a read, we will load these 3 numbers, and we will do disk read on these 3 block numbers based on the bytes. And we will continue to read as long as it returns more than 0 bytes. And because this will not be less than 0 bytes until we reach the end of the file, this will read the entire file on the inode, and it will read blocks 6, 7, and 8 up until it gets to the final offset mark of these 3 files. And then once it's done reading, because it returns 0 bytes, because it has reached its last block, and the offset is now at the end of the inode size. The inode size is also located in the information of the inode table, and the offset has reached the end of the inode size. It will stop reading because it has stopped returning bytes, and we can actually start to close the file descriptor. And all the closing the file descriptor really does is it clears the buffer that was used to load the data from the disk into our data buffer into memory, and it clears that, and it resets the offset of the data block back to its original pointer. And this is basically what is going on in this small block of data. File system level is simply locating where the inode is, and then once that inode is located and what numbers correlate to its specific blocks, at a disk level, we read from those specific numbered blocks and their corresponding data.
So basically, to sum it up, our open function is going to access our inode data bitmap, and our read function is going to access that inode bitmap. And once we are done copying everything over into our buff size, we can then close our file descriptor and continue on if we were to open up another file. Now, going back to our project, some errata and quirks that we struggled on were mostly on the last 7 functions of FS, which was to mount, unmount, read, write, format. All of those functions were very difficult. Most of the bugs that we were encountering had to do with not properly using the disk read and write functions, and we weren't allocating enough memory to store the blocks and access the inodes, which later on led to incorrectly reading the disks and the images, which caused us to fail.
One of the biggest challenges that I think we faced during this project was dealing with bookkeeping in both FS read and FS write, and actually figuring out what variables we need to keep track of when we are reading from a specific offset in certain blocks, and then also transitioning from direct blocks to indirect blocks, but also keeping track of the same offset. Both in read and write, these are very pedantic metrics to kind of keep track of, and it was hard to come up with the metrics in the first place because that bookkeeping is probably one of the hardest things for us to keep track of, but it's the most important upon continuous reads or continuous writes. So that's probably the biggest quirk that we had trouble with during this project.
I agree, and I think what I was able to take away from this project is that our own computer systems have a way more complicated way of storing, accessing, and removing files. This was certainly an eye-opening project to kind of take a peek at to what not only our computers but other technologies around the world use, like video games, consoles, monitors, PC desktops, all of that use the same not the same operating system, but the same disks. And this was really interesting to see how we were able to access all of that.
Good.